So this talk is just discussing application development approaches in Amazon Web Services. My name is Ken Rimple. I work for Chariot Solutions. On the line with me on chat and on Q&A is Keith Gregory. He's our AWS practice lead with many years of experience in various solutions in Amazon and other cloud approaches. So we work for Chariot. Chariot Solutions is a consultancy. Our specialties are developing and architecting applications, both in the front end and the back end. On front end, we've been focusing the last couple of years on single-page applications and native mobile development, more than server-side templated pages. But we certainly have done those in the past as well. And we also have a fair amount of stuff where we move things from one data source, transform them, and then put them somewhere else. So we have data engineering services, everything from simple transformations to, some Spark type jobs and things like that to data pipelining. And we're increasingly doing more and more cloud development, which is why we put Keith in the role of practice lead for that practice. We are a select consulting partner for Amazon Web Services. We are currently in the public sector and education spaces, but we also work a lot in commercial as well, just in general, and have worked with Amazon for AWS for a long time. We did create and we host Philadelphia's Emerging Technologies for the Enterprise Conference. That conference is in its, I think, 14th year. Tracy Wilson-Rossman will probably correct me if I'm wrong there. But that conference is a multi-technology conference that runs for 2 days. We're doing it online this year, and it is being offered for $99 April 14th and 15th. You can watch anything you want out of the conference for the next 90 days. I'll have exclusive access to it then. And then, we'll publish it later on YouTube and places like that. We also sponsor user groups and conferences. And so we spend a lot of time paying attention to those and making sure that we have some impact. And we are also a top workplaces winner for Philadelphia for 2010, 14, 16, and 18 when we put ourselves up for that. So I'm our director of training and mentoring. I've spent all my career at Chariot doing that either externally for our customers or internally for our consultants when I'm a little bit ahead of the curve on some of the newer technologies and want to share, or just to get some consultant up to speed on technologies that they need help with. Right now, my focus is on serverless and Lambda, as well as container-based technologies like Docker, ECS, which we'll talk about. And also, I've spent a lot of time with single-page applications, writing training in React and Angular, and earlier AngularJS for those as well. So that's who I am. Here's what you're going to learn today, or what we're going to talk about at least. So we're going to start by looking at the differences between virtualized, containerized, and serverless development platforms on AWS. We'll look at pros and cons of each pattern. We'll then take a look at some of the elements that make up cost across all the different platforms. And we'll also have some thoughts for you about strategies for migrating, strategies for usage of each approach, and maybe starting to add services from the other approaches into what you're using. This talk assumes some casual understanding of Amazon Web Services. You don't need to be deep into it, and I'm going to be trying to define some terms as we go along, so we'll try to keep them higher level where possible. A couple terms early on. So first type of architectural style we're going to look at is virtualizing machines. And this is pretty much ancient in terms of Amazon Web Services. It's one of the first things they put out is the ability to run in the cloud as a virtual machine. So we're going to take a look at what EC2 virtual machines bring to us and why you might use those. We'll then take a look at containerized applications. We'll discuss how Docker deals with building containers to run inside of engines. And then we'll discuss how Amazon delivers it with ECS and Fargate as one solution. We'll then look at serverless applications a little bit, kind of define what they are, taking a look at Lambdas and what they can do, and also serverless services. If you think about a serverless application, it is an application that is mostly managed by Amazon, and that you write small functions known as Lambdas that are deployed into the cloud environment to be executed either inside of Amazon's platform or to be exposed and executed from a remote call. One of the things that will kind of help us along here is to discuss briefly the shared responsibility model. The shared responsibility model in Amazon, it simply means that AWS is responsible for security of the cloud fabric, the platform for the cloud. So, everything from the hardware to the network connectivity to outside regions to patching the operating environments, all of that stuff, everything up to the point where you actually rent time on something and create something. AWS is responsible for the security of those things that you are provisioning. They're responsible for the fabric of it, the low-level configuration that they manage. But you as a customer, whatever you create, if you have any kind of degrees of freedom in that creation, so for example, a virtual machine, you've created an instance of an operating system with some software in it. You're responsible for managing what's inside of the virtual machine. If you write a Lambda, the code in the Lambda is your responsibility. If you write Docker containers and deploy them, the code in the Docker containers and their network configuration. So any kind of network security that you have to provide, opening up ports, security groups and firewalls and things like that you configure, that's your responsibility. They're not going to stop you from opening up a function to the world and letting it eat your credit card. But they will stop you from having problems with their infrastructure that they provide. So that's the shared responsibility model. And we'll talk about it as we go along in the process here. Let's start with virtualized servers using EC2. So EC2 lets you launch virtual machines in the cloud. And pretty much anyone who's done any kind of software development has used virtual machines. But what Amazon has done is they've basically created a giant set of data centers that stripe these virtual machines across many different computers. And so what you do is you basically grab an Amazon machine image, which is your seed image that starts up an operating system and an environment, and you feed it Amazon EC2, you feed it an instance type, which basically tells the relative power and strengths and features of that instance. Things like, we'll talk about some of that stuff later, but also the configuration, how much memory, how much disk, what kind of configuration settings for things like networking you might have. And so you give it those two pieces of information and you launch the instance, and then Amazon will manage the instance for you. So after that, it's basically a virtual machine in the cloud. For those Amazon machine images, you have a choice. You can either pick an image from the marketplace or some of their base images. And for their base images, you might just take Amazon Linux and install things manually in it. And then you have something running that has your software. That's pretty good for experimentation. You could also go out to the marketplace and find something. So maybe you're looking to experiment with a database you don't normally use. So like TimeStream or something like that. You can go ahead and create an EC2 instance, experiment with it, shut it down when you're done. But you do have to take a look and see whether those instances fill your needs directly or not. Are they recently patched? Do they keep them up to date? What's the license for all the software in the image? One of the things you'll run into is if you rent something like Oracle, you grab a machine image from Oracle, you're going to be paying a fee that Oracle surcharges on top of that for the license. And that can get hefty. So you have to pay attention to what you're using and how much it will cost you. In other cases, you're probably going to build your own EC2 images, Amazon machine images. And so you can use tools like Packer or create an instance of a base operating system. You use Chef or Ansible to configure up that instance to something that you want to be. And then ultimately, you can take a running instance and turn that running instance into an Amazon machine image for your use later. But generally, that's something that's going to have to happen. If you build your own images, you maintain everything about it. So you put it on a particular version of Linux, you've got to update that machine image to an updated version of Linux at some point and publish it, and then stop and start your servers, recreate your servers basically with those new images. If you need to patch the software, that's on you as well. So, you can certainly do it from the running instance. But generally, if you've got DevOps people, they're going to go back and update the image itself, either by launching it, doing the updates and creating a new AMI, or using a tool like Packer or Chef or Ansible. So that's on you. EC2 instances can be scaled, certainly. That's the whole point of having an unlimited cloud, is to be able to scale the servers that are providing it. So here's an example of a very simple EC2 scaling architecture. We've got our internet client hitting EC2 for an endpoint that is one of our servers. We can then have that particular address point to one of Amazon's tools called an Elastic Load Balancer. And Elastic Load Balancers let you forward traffic to one or more, generally more than one, instance of a server. So in this case, we're using it for EC2. You can also automatically scale the service as you find that you're running out of CPU or load, what have you. You can actually tell a scaler in something called an auto-scaling group in AWS to ramp up as you hit certain thresholds and launch additional EC2 instances. And then as they become idle, bring them back down again. Ultimately, you're probably hitting resources like a database. We'll talk about that a little bit more. But in generally, you can have your EC2 instances then wired up to connect to other resources in the cloud, like databases and queues and things like that, and email services. Now, for a database, you could virtualize one, as I mentioned before. You could start up an EC2 instance. That is certainly one option. And when EC2 was first created, more than a decade ago, that's what everyone did. They created instances of all sorts of things in virtual machines, in EC2 instances of databases and things like that. However, just because you have those AMIs available doesn't necessarily mean that's the best way to go about it. Because again, one of the things you have to do is you have to manage all the volumes, the backups, the infrastructure, the scaling, the clustering if you're going to do that. Failover, you have to configure all that in those virtual machines. So that's a lot of work. So, and also patching the operating system in the database or updating your image that you're running it from for the same, and that can get complex. So it may be better if you take advantage of RDS, which is Amazon's Relational Database Services. And what this does is they provide a number of very popular databases, and they host them for you, but they also patch the OS that they're running under. You don't really ever look at the OS. They patch the database service for you. They give you monitoring and alerting through CloudWatch and other tools in Amazon. They let you back up and restore, and they provide services for that. So you can back up to like the S3 storage service they have. For example, you have high availability options. So you can have it that you have an active and a failover database, and you can even do it where the failover is in a different physical data center. They call them availability zones. So that if something dies where the availability zone goes out, it can switch over to your standby and pick up where it left off. So there's a lot of advantages to looking at RDS. And so the first thing I would say is if you're lifting an existing application from either a physical machine or a set of machines in your data center, or from like vSphere or something like that, or VMware, take a look at RDS as an option for where you place your databases. It's definitely a highly recommended option and takes away a lot of the management that you would have to do and configuration that you would have to do directly. So let's now take a look at containerized applications. So containerized applications, and we're going to specifically focus on ECS because it's most closely aligned with Docker, and it's a little less sophisticated than other tools like Kubernetes. We'll talk about Kubernetes a little bit. And we're going to look at the Fargate task scheduler as our example platform. That's the main one we're going to focus on. But if you take a look at the left-hand side of this here, you see our monolithic layered application. Pretend for a moment that was originally hosted in a physical data center or in an EC2 instance, and all of the code is sitting in one, let's say, Java application. If you're a Java developer, Spring. So you've got a web application with business layered code that does your business logic and maybe validation and dealing with that. And then it dispatches calls to a data tier that goes and calls a database. And there's a lot of these out here. We did decade plus of, and more than that, of writing applications that were, in some cases, monolith. So definitely, single process, multiple thread applications that ran as a monolith. Well, you could certainly repurpose that, and or if you're building one from scratch, you don't have to go down this road. You could decide to build different smaller containers, and containers like miniature operating systems. They're not really completely an operating system, but they're almost like virtual machines. They run a process, they've got a file system, and they run it in CPUs. And you could basically set up different Docker containers or image containers. I use Docker as the term here, as the product. You can have one for one slice of your application, like order management, another one for another slice, like customer management, and another one for a user slice of the application, and have them develop at different rates. Then you could use the REST endpoints to float a single-page JavaScript application like a React or Angular or Vue app on top of those, and have them dispatch calls to the various endpoints. This is becoming a relatively popular pattern, at least from the single-page app side of things. If you couple the single-page app in the front end with scalable containers for each of the slices, you can vary the configuration needed to run each slice and deliver them at different rates of change and get more control over things. So to do that, you have to build images. And I'm going to use Docker as my example here, since Docker is the main image concept or image format that we use in either Docker, various Docker scaling groups, or in Kubernetes. So the first thing you do to build an image is you create a Docker build file. And a Docker build file can be a pretty involved little beast, but it has its own language. It's kind of like a miniature build language. You specify, for example, and this is an example of a tool called Aerospike, which is a database server out there. So I just grab their Docker file. You give it a source image that you come from. In this case, we're using a Debian install, Debian Stretch. And so they have a very slim version of Debian Stretch in the Docker universe that you can build servers off of. And then you'll notice there's things like setting environment variables and doing installs. Other things we can't fit on the screen here are things like creating directories, setting permissions, copying files, setting what the actual program that's run is when you launch the Docker container. And you want to think of a Docker container as running a single thing, managing a single process. When the process starts, that's the beginning of the life cycle. And when the process exits, the Docker container should exit. So you build a Docker build file. You then kick off the build command to create an image of the Docker build file. That image is stored in your local Docker development platform. You can then upload the image to a registry or repository. Amazon has one. It's called ECR. We'll talk about it in a minute. So you can put your private ones up there. Before that, you had to upload them to Docker's own repository or install your own repository tool and manage it yourself. Then you will use your whatever Docker or Kubernetes system to launch this container that's stored in a registry and kick it off on a Docker engine. So the Docker engine is some program that runs that can launch Docker containers from images. The other thing you can do, certainly, is just go ahead and grab an existing container from the Docker registry. And so over time, what you want to do is build up purpose-driven containers that do certain things that you need to get done. And then hopefully reuse a fair number of the generic ones. And maybe you're only changing the files it points to, for example, or where it's mapped to when it runs, like a web server. So you can, customize and configure those things and then reuse them over and over again, or launch multiple instances of the same container to provide load balancing. Here's what a Docker image looks like conceptually. So a Docker image is a layered file system with installed services. If we look at the sample here, I'm building something called Chariot HTTPD customer dub. And what this is a web server that would host my customer web server. Now, I might decide to just make this more generic than this, but just for an example, let's say that this was tailored for a particular web service running content for my website for managing customers. And I base that on another Docker image, which is the official Apache image for the HTTPD server for version 2.4.41. And I picked a variant of that that's based on Alpine. And what Alpine is Alpine Linux is a very small Linux container or Linux operating system that's about 5 megabytes in size. It's very tiny. It has the bare bones services needed to do things. And so the Apache image is directly based with that from keyword we looked at a minute ago on Alpine 3.1.1. So I pulled these directly from Docker container build files, which you can find on docker.io to build my image. And as you look, the OS image puts the basic operating system and file layers in for the operating system itself, var, user, set, opt, dev and things like that. The kernel's on there, or whatever it is. It's all there. The base is all there. And then when we install the Apache image, it layers, and I took this from their build, it layers all the different things that it does. So it'll create user local Apache 2. It'll put config in Etsy Apache 2. It creates a user inside of the image www data and a group www data, and it will then run Apache from that user. And then it also does all the launch files, etc. So all that stuff is configured in the Apache image. And then all I do in my Docker image is configure whatever plugins I want turned on, my specific Apache config perhaps, any logging or config settings, any adaptations, any binaries I have to install for any plugins I might use. And that then is my Docker image. So my Docker image is based on 2 prior images, and it's layered as a third layer on top of those 2. And in this way, your own images are relatively small compared to what they sit on. At runtime, we have to set up our Docker engines and fire them up. So let's think conceptually here about having a data center where we have the ability to run Docker on multiple physical engines. And what I mean by physical engines, you can basically attach that concept to hosts. So in this example, I've got 2 servers running Docker engine, and I'm launching multiple containers here. So, and I'm not even looking at scaling here. I'm just looking at partitioning. And the top Docker image, or I'm sorry, the top Docker engine, I'm running a web server like Nginx. It's proxying from it to a REST API. And so I launch an Express server for the REST API. And I may be calling things multiple times and I'd like to cache them. So I decided to install an cache Docker container instance as well. The arrows you see are just the exposed ports. In Docker, you can configure what ports are exposed from one machine to the next. And you can configure kind of a config for the entire platform, Docker Compose file if you're used to those, and define those ports there, or you can do it when you launch the Docker images. So I'm saying that cache will expose port 8080. Express will be able to see that port based on the network I've configured, which I'm keeping out of this discussion. Nginx will see port 8080 of the Express Docker instance. And then on another physical server, I'm running another Docker engine with Postgres and TensorFlow. Of course, this is just a completely arbitrary and not optimal example, but those are then exposing their ports, and then the Docker engine is exposing those out to the internet or to our local network in the data center, let's say, more realistically. And then our Docker engine on the first server is consuming those ports and making sure that we can see them from Nginx or specifically from Express. So the hosts run the container engine. The engines launch container instances from their images. The instances are defined by you or the community, or a combination of both. Docker can expose ports to the engine, other hosts, and virtual networks, and the container can be then monitored by external tools. Docker has a monitoring API, and as we'll see when we get into doing it on AWS, they wire that API into AWS services like CloudWatch. Here's Amazon's tool for managing containers. So this is only for private container hosting. Now, you might use other tools, other repository managers to do this. But the thing is, when you use ECR, it wires into Amazon services. So it's a private AWS managed Docker image registry. You don't install it. All you do is you configure it by saying, yes, I'm going to use the ECR, and this is the availability zone and region I'm going to run it in. and it gives you an endpoint to hit to publish and to download. You will pay for usage. The costs are relatively, actually very low. So the storage fees are like 10 cents per gigabyte per month. And data transfer out, you get 1 gigabyte free, and then the costs increase, but they're very, very low. And then the first year, there's a free pricing tier as well. We've used this on several projects. One of the projects I used it on most recently, Keith and I were working on something, and he did the integration for this. But we took our application, which was developed in a set of Docker images. So we had an image for a React application running on Express, and then we had Postgres for development locally in Docker. And we had some other services as well, like a migration server. And we deployed the Express server in ECR as an image to be launched for our customer. And then when we did a build, we built and uploaded to ECR using a tool called Code Build. And then we could deploy and tell it to, with Code Deploy, in our case, I don't think we use Code Deploy, but we could deploy and publish an updated Docker image as a new container instance for our solution. So we were able to basically on a commit, automatically build and store the Docker image. And then we could say, deploy this thing, and it would update our cloud environment and run the new Docker container. Now, on AWS, you have a number of choices for your container services. So you certainly have ECS, which is Elastic Container Service. That's the one we're going to focus on. And that's the closest to Docker itself. It's basically a Docker implementation, and it scales Docker engines across EC2 instances by default. So if you go and sign up for ECS, the vanilla version, you go in and you configure what your Docker engines look like by picking some level of EC2 machine, some particular level performance of EC2 machine. And then you fire that up and you can start Docker instances from the images, and you can download them from ECR. There are tools in the command line. There's an ECS command line as well. And also you can do it from things like CloudFormation, which is a configuration tool that is configuration as code. Amazon also supports Kubernetes. So Kubernetes is a different container launching service that was built as an alternative to the Docker way of running engines. It takes Docker instances and runs them in a different kernel. And one of the things that it does that's different is it lets you set up pods, which are collections of instances of different types. So maybe you have a stack that you want to fire up that's a collection of 3 or 4 images. You call it a pod, you launch the pod, and that's the lowest level of deployment you have in Kubernetes. You can make a pod a single image, so it's not like it has to be multiple containers. But we're not going to focus on that right now, because what we're looking at is what is a straightforward, simple config that we can use to quickly ramp up container instances and take away some of the configuration needed to manage those instances. So one tool that Amazon created a couple of years ago is Fargate. Fargate is a task runner that is shared across different engines on Amazon. In other words, you can have different physical different Fargate instances running and have them spread across a number of customers or pieces of hardware, unless you dedicate your particular systems. But in case of Fargate, what it does is it takes away the EC2 container concept from you. All you care about is how much memory and how much CPU you want your container to consume. And you just tell ECS with Fargate, go launch that. I don't care what engine it runs on. You manage it. And I'm just going to see that it's there. And I can stop and restart it and destroy it and create a new one. And otherwise, it looks like Docker, but it's running a runtime that is striped across the cloud that you don't think much about. So you can conceptualize it as we have a managed service, and Amazon managed service is a service that Amazon manages for you and gives you some knobs to tweak. Like I said, memory and CPU are the main knobs to tweak here for Docker container launches inside of a ECS Fargate service. And it will manage that for you. Amazon has a number of managed services. The trend now in AWS is to launch things with a managed service, if possible, when you don't really need to pay attention to low-level things like operating system and installing software. So we can just think of our instances as sitting in the cloud and sitting in Fargate, and we can launch them from ECR, container images, and we just run our containers in ECS. So concerns here that you would want to think about if you're going to go down the road of doing Docker and building a Docker container and putting it in the cloud is the level of granularity of your Docker container. And all I'm offering up here is my own thoughts on this based on observation. But some of the things you want to think about are you don't necessarily want to have hundreds and hundreds of Docker containers for a single application, specifically because each one takes up a certain amount of CPU and memory, and you have to launch them for them to be available. You have to figure out what scaling you need for them to be available. And so can you really get that right with hundreds of them? I don't know that I would do Docker with microservices and every single microservice a different Docker container, but people would argue with me about that. So that's one thing to think about. You may not want to go super granular. You may want to have a vertical slice. In some cases, in the case that we used Docker most recently for, we just hosted an express service, running our JavaScript REST endpoints that went to a database, and we hosted the whole thing as a Docker container because we didn't have a ton of users, and we could scale up based on instances where needed. If we wanted to, we could have broken that up even further and broke up the different slices by different functionality. You do have to manage the network visibility between the nodes. It's good to debug this on a developer workstation first. So one of the things you'll do in a Docker-based development environment is you'll have your developers using the exact same thing that your servers are going to use in the cloud, just different levels of scale. So the machine images are going to be the same machine images, and you're going to launch them the same way. So you'll run the Docker startup on it, like Docker Compose. You'll launch all those services, and you'll test them. And if you use something like Docker Compose to configure your networking, you can troubleshoot that right there. And then when you go to the cloud, at least that's been eliminated, and you can start working on other concerns. And those network ports should be open properly. Each node may or may not need access to some Amazon services. Thinking about this a little bit more, let's say you had a solution where you had one container that was a app server that went to a database, another container that was a server that worked off things from files in S3. You wouldn't want to just take one generic configuration and apply it to both. From an Amazon perspective, you wouldn't want both to have access to the same large number of resources. There's a principle of least privilege that's out there in Amazon's guidebooks that you should read up on. Basically, when you're setting up a container, you want to think about the things that it needs to access and only give that container access to those things. If it doesn't need access to S3, don't create any kind of connection to S3 for it. If it doesn't need to access a database, don't provide access so that it can see the database port. And again, you can do that if you're going down the Docker approach. If it's just Docker containers communicating with each other, you can do that from the Docker configuration. It's when you start pointing out to Amazon-based services that you'll have to set up permissions, and you'll have to use the Amazon's SDK, which requires you to have a role and a user attached to the execution. And when you do that, you need to make sure you limit what that role can see. And so you don't over allocate permissions to things that don't need it. Now let's talk about Lambdas and serverless. So first thing, before we do anything at all, Lambdas are, Lambda as a programming concept just means basically a function. And treating functions as first-class things in a language. Lambda in the AWS term is a function that runs in the cloud. You deploy a function in whatever language that they support, and there's a number of them they support. Pretty much anything you're interested in writing it in generally, unless it's some bizarre language that, like Forth, you're going to be able to run a Lambda for it. You create the configuration for the Lambda, and you deploy it to AWS. Serverless applications hook up nicely with Lambdas because a serverless application is meant to not really have you manage it. So you don't think about managing a serverless application. You think about twiddling the knobs that the serverless feature or application will give you. So, for example, with Lambdas, you would manage the permissions in identity and access management. What can this Lambda do? What can execute this Lambda? You configure the network access. What is it allowed to see? Can it access a resource in S3 on the network? Where can it go? Is it exposed to the outside? You deploy Lambda code and you update the Lambda code by redeploying it. So there's the mechanism you have to manage for deploying your code in Lambdas. And there are tools out there like AWS SAM and Serverless and some other ones like Architect that will kind of put a nice wrapper around this and make this easier to do than just doing it from either command line tools or a very large CloudFormation script that can shorten those. But you manage those. And then also you define the biggest knob that you can turn in a Lambda is you can turn how much memory you can allocate to a certain point. And what that does is it decides how much it's going to cost to run your Lambdas and how much of a CPU it's going to give them at that time. Amazon itself in AWS manages the execution engine for Lambdas. So right now there's a VM out there called the Firecracker virtual machine. And that is something that they built to run Lambdas in AWS. And they run these Firecracker VMs across hardware in their data centers, and they hand them off ready to go to you. So Firecracker can immediately run your Lambda, but then the Lambda has to launch, and that can take a little bit of time. We'll talk about that in a minute. But that's Amazon's job. And it also manages the CPU allocation. How much am I going to get in terms of fraction of CPU, the launching of the instances themselves, and pruning any idle instances that might have been executed once but are sitting out there for an hour and need to be shut down. Some other managed services, just to give you a flavor for other things that are managed by AWS, where the responsibility shifts to them more, are DynamoDB. If you use Dynamo, you're using a database as a service, basically, and you're using it as a managed service. It's a database engine that does document-based databases. It's great for storing document-based storage and looking up things later. It's not the best thing for doing anything like a data warehouse or large queries against giant data sets because it can be slower and it can be expensive to do so. But just as an example, that's one. You've got Dynamo tables that you manage. You configure indexes. You configure how available and how performant and how reliable is my table when I mount it. And those are the kind of knobs you twiddle. And Amazon manages the actual storage behind the scenes and the query engine. Simple queuing service, it's one of the older ones. And so that's a queuing engine. So is Dynamo, actually. And so if you want to put a queue out there and you want it to be used by more than just one thing, you might start by taking an EC2 application, pulling the JMS-based queue off of that and converting it to SQS, and then have a Lambda consume the messages from that queue. And so now you can externalize access to that, what was its own little monolith, and start getting messages out to Amazon-based cloud services by subscribing to an SQS queue in a Lambda. You might publish a message in a Lambda and so on. And those are some of the things you would twiddle there, as well as the queue settings. But you're not actually physically installing a queuing service. Amazon takes care of that and patches it for you. AppSync is another one. AppSync is a GraphQL data API that has client-side data syncing. And what it does is it provides a GraphQL endpoint that then maps to things like Dynamo tables or data in S3 or a Lambda. So you can actually have it trigger a Lambda to run and return data from a client using the GraphQL query language. And that is something that's becoming more popular. That's another managed service. And there are tons of them. There are ones out there that resize your images for you. There are ones that transcribe text for you from audio. And so there are a lot of managed services out there. And the way you'll know it's a fully managed service is if you don't have to ever specify things like a virtual machine type and size. We were debating, Keith and I, about a little bit about managed services. And I brought up SageMaker, but he reminded me that you do have to configure the instances and launch instances for SageMaker. So that's kind of a somewhat managed service. And also RDS, you do have to tell it the size of the databases you use in most of the configurations. It will launch those databases, but you do have to kind of configure them a little bit more than you would a fully managed service. So they're kind of on a blurred line there. Now, what can Lambda functions do? First of all, you can do the traditional thing, and what a lot of people are doing with their hello worlds out there is you can wire up a Lambda to respond to an HTTP endpoint out there. You can use API Gateway, which is something you can map an end request to any service you want to in AWS. That makes sense to do so. So you can map it to your old EC2 service endpoint, and then as you start replacing those, you can start putting those pointing those to small microservices in Lambda if you'd like to. So you can also use an application load balancer if you wanted to have a whole lot of these instances running and provide those. It's another way of doing it. And you can have it respond to events in AWS. I think this is actually one of the bigger uses of it for most organizations, specifically because at least over the last couple of years as it came out, there was an issue with how long it would take to launch something and get an answer back if the Lambda wasn't already woken up, or if the one that was woken up was in use. They try to give a little bit of time to a Lambda to live before they shut it down. And so, they weren't thought of as much for things like web servers. They were thought of more for like glue in the enterprise. So you could say, I would love to know when an S3 bucket was changed. And so if I can find that out, I can run a Lambda to do something about it. Maybe, to run the SES email service and email an organization that a file arrived, or put a message on a queue. Same thing with transforming incoming data. You can say with Kinesis, which is a data pipelining tool in Amazon, you can have the data pipelining tool notify a Lambda to transform the data to then put on a different destination. You can execute a trigger when something arrives on a DynamoDB row. And again, respond to a GraphQL query and return the data. So there's a lot of things you can do with Lambda functions. It's great for handling events in AWS, and it's also good and getting better all the time at handling HTTP endpoints. Let's look at the endpoint case for another second here. So the endpoint example would be maybe I have API gateway that's serving an application, or at least endpoints in an application. And I've got requests coming from a client in the internet that are posting to say /customer or /customer/resume. And what they're doing is they're posting information about the customer in a more JSON document format. Lambda function can pick that up and insert it into a Dynamo table. And you can do validation and things like that, return a failure when it's wrong, and do all the things you need to do for that kind of operation. Maybe there's another post where you upload the resume itself. In that case, you might want to store it in a storage bucket, S3, Simple Storage Service, which is their serverless disk storage that can be exposed to applications. In fact, you can even use S3 buckets to host web servers. And so when you build your React and Angular applications, you can host them from S3. This is a quick side note. Now, this would be an example of handling a couple of endpoints from a Lambda. You could do that, certainly. You could also glue things together with Lambda, like I said before. So it's a really good utility for getting things done. Let's look at some of the key concerns. Your provisioning necessarily becomes fine-grained down to the Lambda. If you were using before Docker containers, and the Docker container was doing, a vertical slice of an application, that vertical slice might be 7 REST endpoints, 20 different logic functions, and code to get to those database resources all in one container. And when you deploy it, you're deploying that nice chunk of code. If you write that as a series of many Lambdas, each Lambda must be deployed. And, each Lambda must be deployed, and you have to reason about its security, its rights, and how much memory to give it, and so on. So just remember that. You may decide to put more code in a Lambda than you would in a simple service because you may want to have less Lambdas and have everything local to the Lambda. So you might have the parsing, the business logic, and the data access of a single thing in a Lambda, as opposed to 3 Lambdas, one of which is front-facing, just because it becomes a nightmare to deal with that many pieces of code to be deployed individually. Cold start latencies can be a concern. As I mentioned, when you start up Lambdas, it has to initialize the Lambda. It has to grab a Fargate, a Firecracker VM, as we mentioned before. So it has to grab one, assign a Lambda to it, and then it runs the code that you point to for your Lambda. If you, in that code, connect to a database before running the Lambda, you can then, every time it wakes it up again, if it hasn't been, thrown away, that connection is still active. But it takes time to create that connection. So all these things can contribute to latency. It used to be a real issue with virtual private clouds, VPCs, where you carve up your AWS account into smaller targeted clouds that are isolated from each other. It took longer to launch a Lambda in those because it had to provision an IP address, and that took time. And they've made that much, much faster now. It's down to, hundreds of milliseconds in most cases to do that kind of thing. But they have other things that you can tweak as well. So we'll talk about that in a little bit. Just remember accessing stateful resources like an RDS database connection can be wasteful if you do it every time the function runs. There is an option here. So, for example, DynamoDB, yes, one option is put everything in Dynamo, but maybe you don't want your app in a non-relational database. Dynamo has its own weird quirks. If you're doing select star from and doing group bys and things like that, you're going to miss it when you go to Dynamo. So one thing you could do is you could deploy the RDS proxy. Amazon has this service, and if you think of it conceptually as a connection pool in the cloud that's warmed up and ready to go, you're connecting to that from a Lambda is very, very quick. Now you'll have to pay for it, and there's pricing on the page for AWS RDS proxy. But it may be just exactly the thing you need if you want to have very quick, low latency access to a relational data source like Postgres or MySQL or Oracle or SQL Server. Another thing is you do have limits on the number of concurrent Lambda executions in a given region. And so I believe it's 1,000 by default that Amazon sets, and you can contact their support and you can get those limits increased. But if you're hitting 1,000 concurrent Lambda executions, that's something you want to get a handle on your costs and see if that's exactly what you want to do. If you give it a low amount of memory, if you write the code in an inefficient way, if you do things that could be better done in a SQL query, for example, fetching a lot of data and filtering it in a Lambda, that's a no-no. If you have to filter it and you can fetch it with a where clause, use the where clause. That's never changed in 20 years. Get the least amount of data possible for the Lambda to function. So take a look at why they're running so long that they're hitting concurrent accesses. Just a quick tip there. Okay, so now let's look at the different approaches and compare them. So going back to EC2, looking at the pros of EC2, it runs anything in general that a virtual machine can, which is a good thing. You put together a virtual machine, let's say in vSphere. There are facilities in AWS to port a vSphere virtual machine into EC2 and make an AMI for it. So that's great to know. So you'll have minimal changes to lift it into AWS, provided that the services it needs can all be also elevated into AWS or replaced with services like RDS or other services that are available in AWS. So in that way, it allows you to have a gradual shift to AWS infrastructure. You can get onto it if your data center is being decommissioned. You can get into it with virtual machines and slowly move to other architectures as it makes sense. Clustering and balancing and auto scaling are all available for it. Monitoring is there. And so it's a very robust service. It's the oldest service, probably next to S3, that Amazon has. So talk about something that's been, debugged to death. That's a good thing. You manage the operating system and platform on the con side. If you grab a Oracle database instance and you launch it, you have to contend with the fact that now that EC2 instance is your problem. That means that if the operating system that's running under needs a patch, you either have to shut it down, get the updated AMI for it with the patched operating system, or patch it yourself. Same thing with the software it's running. It's running Oracle. Let's say you go to Oracle Bleem, and Oracle Bleem doesn't have, you don't have support for it in the AMI. Do you have to roll your own update to Oracle Bleem? Probably do. So just remember, you will own it. You will own the software upgrades to the platform on the EC2 instance. You pay for each minute of operation, and you can choose to pick different allocation types for EC2. So you can tell it you want a more burst oriented EC2 instance, and you'll pay for the burst at a higher rate, but you won't pay nearly as much for the idle time. I would highly recommend you learn the traffic patterns of your applications and then go back and look at EC2's machine types and see if you can switch your instance to running a different machine type that's more cost effective for you. Maybe you over provision memory and you're only using a third of it. Man, you're paying for that. So if you could monitor your database and find out you could drop it by half or 2/3 or whatever, you might be saving, hundreds of dollars a month, depending on the size of that image. So that's something to consider. You have to manage the infrastructure and the application itself at different. They move at different rates, right? So the infrastructure would be things like if I'm taking as an example, Oracle or MySQL. So that's the infrastructure for your application, or maybe Express, let's say, make it simpler. So you're doing a web server in Express. You have to manage what Node.js instance you're running, what Express version you're running, and you have to deploy changes to that somehow through a set of scripts. Maybe that's using Chef. And then the application needs to be updated, and that would be done through something like code deploy and by copying the files into a volume, an EBS volume somehow. Those are all things you have to manage. And you have to manage both of those because you are managing the whole thing. Your logging needs integration to go to the cloud infrastructure. So yes, you get logging for the fact that the machine launched and it's getting this rate of performance in CloudWatch. You can put up CloudWatch alerts, and you can do things like configure the auto scaling based on your load, but it's not taking your application logs. So you will have to adapt into some sort of logger, whether it's Splunk or Elk or CloudWatch, and set up adapters to those and make sure you set the right permissions and rules and APIs to do that. For containers, certainly you can separate concerns a bit better, and you can kind of have purpose-driven containers. For those one-off things that can consume a lot of your CPU, like running, machine learning or generating PDFs, you might make separate Docker servers for those purposes to keep the traffic off of your REST server, for example. And that's a great example. You can scale horizontally. So you could say, I want starting with one instance of my web server, and I want the web server to grow to up to 15 instances, and then scale back down to one. And this is the rate of change that I want. So I might want to scale down slower or faster. And that's something you can do in EC2, but with EC2, it takes time to start a machine. And you're paying for an entire machine. With Docker on Fargate, with ECS on Fargate, it's just going to have that Firecracker VM grab the image and create an instance really, really quickly. So it can ramp them up very quickly and tear them down quickly as well. You also have native CloudWatch logging. The Docker containers standard output of the process you run and standard error are logged to CloudWatch. Done. So that takes care of that. You can get more sophisticated with it. You can install like Log4j in Java. You can install different logging things to do different ways of doing your log. But bottom line is that output is there. Things like the access log, though, for a web server may not go to it. So you may have to do a little bit more to send the access log from the web server out to CloudWatch, for example, if you care about it that way, or copy to S3 or something. Developers run the same platform as production. This is a huge reason to use Docker. And the reason that developers like it is because they don't get surprised when you go to production readiness that, oh, you never really thought about what the connectivity is between my 5 different Docker instances. And with a monolith, in many cases, The developers develop on their local machines. They sometimes develop against different databases because they don't have the licenses. It can be a real nightmare. If you're using open source software and you're using Docker to do all the development, it's a relatively straightforward lift to move it into ECS, and it's just twiddling a bit to turn on Fargate. And containers are portable across platforms. One of the nicest things about Docker is Docker images are either Linux-based instances or Windows-based instances for those of you who are on Windows. And pretty much even on the Windows platform, they default to Linux containers, Linux instances. So, I was working on a Surface Book doing my development in Docker, and we were able to take those same exact images, which are Linux images, and place them in ECS using Fargate, and we just had to tweak our memory and CPU requirements when we deployed it, and that was pretty much it. The cons, those Docker build scripts. Someone's going to have to become an expert in it. It is not insurmountable, but it is not an infinitesimal. It's not a tiny little amount of time to spend. There are people that wrestle with these things. A really good Docker developer is worth their weight in gold if you can find one and put them on the project. And they're worth it. They're really worth it. It's a really kind of cryptic platform for someone coming into it from no experience. So just keep that in mind. But it can be really rewarding for the way you put together your software. The networking is more complex. I didn't really cover this much. I maybe mentioned the word networks, but Docker lets you set up virtual networks. These are basically ways of segmenting your network off in a multi-container configuration. And you can do that and use the same virtual networks in ECS. But you have to learn how they work. And again, it's not insurmountable. It's just something to learn. You may have orchestration complexities, like launching a container may be predicated on the other container starting up. An example of that is we had in our application recently, we were using a migrations tool to update our database in development, and we ran a Docker image of Postgres in development. So we had to make sure that the Postgres server was running and could respond to a query before we actually initiated the job of the Docker container for the migrations. And you might do the same thing for when you run in production. You don't want to kick off a job until you make sure that you have an active database and an active queuing system and so on. So you may end up having some container monitoring built in that you have to work with. And you do pay for idling containers. That is something you have to think about. And you do want to think about maybe scaling groups to scale way down to 1 or 2 containers if you have a lot of idle time, just so you're not paying so much money. If you're not using Fargate, so you picked ECS or the Kubernetes EKS, and you decide to use EC2 containers, the pricing is based on the EC2 instances that run the Docker engine or the Kubernetes engine. So you'll pay for those as well. And I recommend, if you don't have to go the EC2 route and you can use Fargate, if you're just getting started with working on Docker in the cloud, definitely use Fargate at first and see how far you can get. You probably can eliminate a lot of administrative headache and get that scaling and that quick launch. For Lambdas, pros, they are great for event processing and gluing things together. You don't have to do any OS or platform management. Firecracker is their problem. You don't worry about that. And in fact, they keep tuning it and they keep releasing updates to it, and they just deploy the updates so that everyone gets it. They do it usually by region, so some regions go first. And they have bulletins about these things and when they're changing. But the thing is, you don't have to think about that. So great, that's more of the shared responsibility shifting over to Amazon. And that's a really handy thing. You pay per invocation of the Lambda, and you pay more based on how much memory you allocate to it. That also means that it runs faster. So if it would run slower with less memory and runs faster with more memory, it may be a wash. So it just depends on how you write your code. And you have cloud native logging, just like you do with ECS. All of the output of any, logging output, like console log and things like that, and system out print line or, log4j log to standard out, they will all go to CloudWatch. And you can trace your invocations with AWS X-Ray. You can select for each Lambda that you want it to be traced with X-Ray, and then it will give you a tracing section on CloudWatch, And you can drill down into all the steps that the Lambda took from its initial, call from maybe an API gateway or from, wherever else it came from, all the way down through the layers that it consumes to what it's doing and how long each of those took. So you can get a real, and also the errors are embedded in there if it fails. So you get a real feel for what happened and where it failed. And that's just one click to turn that on. And you turn it off when you're done. The cons would be if you are using Lambdas and you're making everything you write a Lambda, you may want to stop. You can think of Lambdas as a way of running the code you want to run. You can have them use shared libraries from your language. So, for example, I could use a Java jar, and I could deploy the jar with a Lambda. Now, a warning there, the larger the thing you deploy the Lambda, the longer it takes to start up, and the more memory it takes. But if you're just sharing code from Lambda to Lambda to Lambda, you could share the code either by using a library from your original source, or there's also, for things that are wrapped around your Lambda before or after it executes, they have Lambda layers. And layers let you have shared code for things like logging and auditing and managing setup and cleanup. So you may want to look at using layers for things like your database connection and your logging to take care of that. And maybe you have less Lambdas in the end. There's less code for sure in a monolith than there would be in a multi-layer application than there is in a ton of Lambdas all communicating with each other. So if you go too fine-grained, you are now tied with your giant Lambda net. So try to make these a little bit more coarse-grained than you would think of them as, and take advantage of reusable code either from your languages, libraries, if they're small, or from Lambda layers. And you have less provisioning in a monolithic container. As I said, the container is probably a little more coarse-grained to begin with. Each Lambda has to have its Lambda configuration, so that can get tedious. Just taking a quick look at cost factors, and you will get these slides, by the way. I'll send these out as soon as we're done. I'll generate the PDF for you. So if you take a look at some of these factors along the left here, data transfer and such, we're going to look at these by each particular type. So we look at EC2 here. You will pay for data transfer. Anytime you take data out of an EC2 instance by querying it, by sending it off to something else, maybe you're throwing it into another region for backup, what have you. If you are sending it to a web service, if you're sending it to S3, you're going to pay for that. And you're also going to pay for the S3 storage to hold on to it ultimately. For EC2, the time-based costs are by instance type. I do have on here, let's see. Hold on. Darn it. There we go. So if we just take a quick look at EC2 on-demand pricing, we don't have to get into too many details. Just take your eye on the right-hand column and compare it to the left-hand column in this thing. So you see on the right hand, it says Linux, Unix usage. And you can see that as we go from different container types and sizes upward, the costs become more intense. For example, if you decide to use an M5D 8x large, it costs you $1.80 an hour, and that's 32 gig, processors, 128 gigs of RAM. I'm sorry, what is it? I'm sorry, that's the current generation. 128. Wow. 128 processors, 128 gigs of RAM. And so that can be significant. But these can get really pricey really quick if you pick the wrong one. For example, you really want to pay $4 an hour. If you need that kind of processing, you do. But they can be costly. And so what we see here is there's different types of computing platforms, right? The general purpose one, I'll find that first. And I'm scrolling here. I apologize. There it is. It was right in front of it. So the general purpose is one form. And so what's happening is you have different types of processing that you'll do. If you don't know what you're going to use, you'll pick general purpose. If you know that you're going to be doing heavy CPU intensive operation, compute generating operation, then you're going to be focusing more on the number of processors. So for example, here's one that's $4 an hour, 375 processors. That's crazy, but you might need it for something. GPU, if you're doing machine learning, you can do it on GPUs. You can rent those. And they have them in Intel and also in their own chipset now, in addition to the other processing. If you're doing things that are very highly memory optimized, like caching, there's ways of paying for those and having high speed memory access. So the point being that there's no one way to tell you what the costs are going to be, but you can definitely expect to pay per minute for the instance type, and then they have an hourly rate that you calculate based on that. You will pay for load balancing in basically all of these if you use a load balancer. So there's costs for the load balancing, and they break that up into numbers that they document well on the site. There are storage costs for EC2. If you create an external volume that you want to keep, even if you destroy the instance and bring it back again, and maybe that's where you keep your application code, then you're going to create that as an elastic block store volume and attach it to an instance of EC2, and you're going to pay for that. If you're connecting to the outside world from the EC2 instance, you'll have to set up a NAT gateway, and that costs money. So those are examples of some of the factors in EC2. You can go for all of these things. You can go and you can look at the cost estimator. It's called the simple cost calculator, I think it is. The problem with that is it's just an estimate, and it's very general purpose. It assumes a lot of things. So in general, as we're looking at these costs, you'll want to pay attention to what your spend is. So there's the AWS Cost Explorer for that, and you can look at exactly what you're doing at any given time by looking at that. Looking at containers, ECS with Fargate, you do pay for data transfer out and across availability zones and regions. You will pay virtual CPU cost and memory cost per container that's launched. If you're a Docker person, by the way, you can think of, there's your Docker configuration for running multiple Docker instances like Docker compose.yaml. They have some custom settings you can place in their own YAML file that you can also configure in CloudFormation or other tools that say, I want 4 CPUs for this particular container. I want a gig of memory. And then you basically give it those settings, and it launches them that way, and it bills you accordingly. You don't pay per number of invocations for either of these two because they're servers that run, and you're paying for the server or the instance of the container. You will pay for the load balancer in this case if you're going to expose it. Docker, you don't normally write to the Docker instance file system for anything that you want to keep. A, it's slower than writing to something else. And B, it's not meant for that. So with Docker, they have the concept of storage volumes, and there's a number of ways of configuring those. In Amazon, one of the things you can do is you can create an elastic block store volume, and you can attach it to Docker as a path in your file system, in your layered file system. So maybe you put your logs there, maybe you put your data there, maybe you put some application code that you want to keep or something there. File uploads from customers until you can put them over in some place like S3. You'll pay for those. And you'll also pay for ECR storage for your containers, images when they're stored in the repository. And of course, the NAT gateway, if you're going to use that. For Lambdas, and by the way, that means also NAT gateway, same thing. If your Docker instance needs to communicate with the outside internet, it'll need a NAT gateway. For Lambdas, you're going to pay for data transfer out of the Lambda because pretty much that's the Lambda's running your code, and then it can only send data in or out. And so without that's anything coming out of the Lambda, you're going to pay for transfer to wherever it goes. You're going to pay time-based costs for gigabyte seconds. And if you look at the pricing model for Lambdas, they get into like how much memory and such makes up the cost for any level of gigabyte seconds. They give you a month free. That's not correct. They give you 1 million invocations free a month across all of your Lambdas for, I think it's for account. but the bottom line is you are getting some chunk of free time up to a certain number of gigabyte seconds. I think it's 400,000, but I could be wrong. And if you decide to use load balancing as one way of accessing the Lambda, you will pay for that. Generally, you use API Gateway to access the Lambda from the outside world, and that's not necessarily something you'll have to worry about. Storage cost-wise, you don't really have a storage in Lambda external to it, so we don't worry about it. If you want provisioned concurrency, where you warm up your Lambdas and keep them warm, and this is really important where you want to put a front end on your Lambdas. If you're kicking off a job at night, who cares if it takes 30 seconds to launch a Lambda? But if you're hitting a web server to say, give me a graph, it better darn well come back quickly. Better not take 30 seconds to launch it. So, and I'm giving that as an extreme example here. But you can have it warm up your Lambda and have it ready to go to a certain number of them, and you'll pay for that. But it may be better to pay for that and get the low latency than it would be to not pay for it and have lost customers. You'll pay for a NAT gateway if it needs to go out for that, and you'll pay RDS proxy fees if you decide to connect to something like Postgres or MySQL or Oracle or what have you through RDS. You can use the RDS proxy, and you will pay fees for that as well. But again, it's a quick connection as opposed to what it would take to have an initiated connection and tear it down on the server itself. And just briefly, the biggest thing you can do here is look at the Cost Explorer. And the Cost Explorer, it will let you drill down and take a look at all of your data, what your spend is across all of the different services that you're using. So, for example, if you end up using a ton of S3, you'll see it. If you're using one Lambda much more than the others, you'll see a spike for that. If you forgot to turn off, I'm guilty. If you forgot to turn off an instance of something like SageMaker, you'll see that that's costing you money. Well, as you're tuning these approaches, you'll take a look at the Cost Explorer and you'll tweak it and you'll look at it again. A thing that I would recommend, and I got this from Keith, Keith strongly recommends this, is tag all of the things you create in Amazon Web Services. There's tags that you can label things with. And the idea is you can use those in things like Cost Explorer and in CloudWatch and other places to filter down things and see only what you want to see. And it really helps you analyze things. So don't do that as an afterthought. Definitely have a tag for each of the applications you're building, for each of the major features or services you want to do. You can do it by the group that's doing things as well to keep track by cost by group. And so we use it, for example, for our sandboxes to say, you can get rid of this after some date. We're almost done here. I just have a few more things to say. And if you've dropped off, my apologies. Breaking up the monolith. So if you decide that you want to take a monolithic application and break it up and put it in AWS as a series of, Docker images or Lambdas, just consider whether it's financially worth it to do so. It may not be. It may be that it costs more to write the code that replaces your original code, and it may not ever bring you back the benefit of the savings that you thought you were going to have. And you could scale it better in the cloud by running multiple instances of that server and load balancing it. But one thing you could do is not think of it as breaking everything up. Take pieces out of it that you could externalize and use in other apps. I made the mention earlier about using SQS for something. So it certainly is a good idea to expose things in AWS that you could use in other places, and then replace that piece of infrastructure if it's a small surgical thing to do. And definitely don't do it if the application performs fine, because what's the point of rewriting something that works? It doesn't make sense to me. Unless the only reason to do it is because no one knows how to write the code anymore. That's a viable reason, for example, because maybe it's an old platform or it's at the limits of its scaling. But that's not what I'm talking about here. If you start with EC2, consider using RDS for your database. We can cover that enough. You could migrate your security. So if you've got single sign-on, for example, and you want to be able to provide sign-on to your application, and it was using OAuth or LDAP, you could wire that up with AWS Cognito. and have even Cognito itself be the front page for signing in your application. Then you could start using Amazon's identity and access management to manage that application if you wanted to. You could set up your log adapters to point to CloudWatch or maybe Splunk or Elk or something else. You could move static web hosting to S3 buckets and CloudFront, as I mentioned before. This could be a big help for you if you have a lot of static content and you were serving it through, let's say, a Tomcat server in Java, which is definitely not the way to do it. Migrating services to managed service where appropriate. We already covered that with things like queues. And consider maybe some monoliths could be broken down into containers. If it's a simpler application, if it's something where there's a clear delineation of features, maybe there's multiple web applications, and maybe they're all running on the same Tomcat server and they just use it as an aggregator. And I've seen this a lot where they have, 5 web apps running on one Tomcat. Great, create 5 containers running Tomcat. Each of them run Tomcat, launch 5 different containers, and you're done. And you can consider Lambdas for things like integration as you start putting out to managed services. If you're starting with ECS and Fargate, focus on the redundancy and scalability. Make sure that you have multiple container instances. That way you have some reliability there, and scale it up. Maybe consider creating another version of this config or another copy of this config in another availability zone you can switch over to in case you lose yours or another region. Understand the language and platform restrictions. So when you build a container on a language that does single threading, like Node, you're going to have a single thread per container when that thread is active. Remember that. Java is a multi-threaded process. You can tell ECS, I want 4 CPUs. Well, if you set 4 CPUs up for a Node application, you just wasted 3 CPUs. So just remember that. You're not really going to take advantage of those other CPUs if the event loop is taken up. You could do things like launch PM2, which launches multiple instances of Node. And you could launch 4 instances of Node in a 4-by container. Or you could launch 4 containers with 1 CPU. So these are things you'd have to experiment with to see how you can maximize your concurrency. Or get a language that has threads. Select appropriate AWS managed services. So where you can, make sure you're using managed services to limit your amount of work that you have to do to manage them and back them up, for example, with RDS, and consider RDS proxy, when you get to Fargate anyway. Or so we need the Lambdas. And ECS Docker is great for horizontal scaling, meaning more instances, but not so much for active passive failovers and things like that. That's what databases need. And so you really want to look at things like RDS for that, or EC2 with manual config if you really have to, for a database that's not running on RDS. Not everything is a Lambda either. So when you start building Lambdas, as I talked about before, don't go crazy. I think we covered that pretty much to death. So we're gonna fix that. We're gonna move on. And as you move up to these more managed approaches, containers break down so that you're not dealing with a giant operating system and launching an entire VM. So the management of the containers with things like Fargate, that's on AWS's side to manage and patch and deal with. When you get up to serverless services, Amazon deals with almost everything. You just have some knobs to turn. And with Lambdas, you're just running functions in the cloud and saying how much memory they want to take up. So the more you get abstracted away, the more Amazon takes care of. And that's one potential benefit of getting away from EC2 in an AWS application. All right. Well, thank you for sticking around. The slides and a video of this event will be online shortly. If you're interested in training, we are running a training course, and we're looking for interested parties. We'll do it online for now, given the current situations out there, but we can also come to you when things settle down. It's at chariotsolutions.com/AWS training on AWS fundamentals. Register for ETE. It's $99 right now at phillyete.com. We'd love your feedback. And I put a page of helpful resources out there that we'll mail you as well, that are links from our talk that hopefully will be handy for you to take a look at. Thank you.